Hello everyone, you are welcome to Messed Up Mentors. This is Python for chemical engineers. In this episode, our discussion will be centered on dynamic optimization using simultaneous estimation GEKKO. If you are new to my YouTube channel, please subscribe to my YouTube channel and you can as well check out my other videos on my channel. So let's go straight to the subject of today. Start with, we will import our respective packages, which is a matplotlib for visualization, numpy for handling our arrays, and the package which we're going to be using in discussing this topic, dynamic optimization. So we'll import GEKKO, or say from GEKKO, import GEKKO. Now, I've discussed extensively the package GEKKO in my previous video. If you have not seen that video, you can check it out with this link. In our first problem here, we will be solving this first order differential equation. So we have our dx dt equals minus kx squared. To solve this problem, first we import our respective packages and then we'll proceed to solve this problem. Now, to solve this problem, we will call or initialize the package GEKKO by assigning that to a variable m. So we have m, which is like standing for an abbreviation for our model. So we have m equals GEKKO, and then you can either use GEKKO with remote equals true or remote equals false. Okay, by default, the remote is true. So here I use remote equals. I think I would advise call GEKKO and use the remote server to solve your problem. So the next thing we're going to do is that because we have a derivative with time, we'll define m dot time. In other words, we want to define the time variable, the time space, and that will be np dot linspace. I will take any linear space vector between 0 and 9, 101 of it. The next, we define the value of our constant k, and then our variable x, which we are going to define by calling m dot val, which is var, and then we'll choose an initial value of 2. It's just an estimate, a guess. So once we choose an initial value of 2, the next thing we'll do is to write our differential equation which we want to solve. To do that, we do m dot equation, open the parentheses. The derivative is defined as x dot dt equals to minus k, and then you have x squared. Now, the next is to choose the mode of solution, because here we're doing solving the differential equation. We'll use simultaneous estimation. So we choose our option as m.options.i mode equals 4. In my previous video, I discussed extensively the different I mode or mode to solve when using a package GEKKO. You can see that using this link. Here, because we are doing simultaneous estimation, we simply will use I mode equals 4. So next, we call the function solve, m.solve, and here we don't want to display our solution. If you don't pass an argument, display equals false, automatically it chooses the default argument display equals true, and then it prints the result while you are solving it. We're going to test options. Having solved this, what we need to do next to visualize our result. So I called plt.plot m.time to pick the time variables and plotting the values, output values of x against time. And then that's why I have m.time, x.value, and then I, of course, using the respective options, my line space and then an asterisk with the blue color for the line space to plot my result. Then define the y label, the x label, then I show. Run this cell, we should have our results printed in a short while. So this is all the solution of that differential equation. You can see in this place that the result is not printed. If I remove display equals false, by calling this, I use the default argument. What do we have if we run this cell? Watch what is happening. You see our solution is printed, and so you see the number of state variables, you see all of these solution parameters, the method which is being used, and the iteration, number of iterations, and it goes on, and then you can see here the final value of the objective function 0.0000, which is then we have our plots displayed here. Now, let's look at a second ordinary differential equation here also as our problem 2. Here we are solving this ODE, which is k dy dt equals minus ty. Now, again, in this case, I want to use call GEKKO by using passing the default parameter remote equals false. So I want the parameter remote to be equals to false. So I'll call m equals to initialize GEKKO, the GEKKO package again. This time around, remote equals false. Unlike in the first problem, we use the default argument, which is remote equals true. Again, define our time space. You can use any definition. I use 0 between 0 and 90. You can use as it suits you. Then I define the value of k. Here, my k is 200. The value of k will be given to you in the problem. Define now my y variable y is m dot val. I choose an initial value of 5, just a guess. There are other options we can pass in here. If you want to look at that, I don't want to discuss that in this video, so as I don't just extend the length of this video. But you can check out my previous video on this using the link. So now the next thing I'll do here is to define a parameter t. Here I'll call m dot param, and the value will be my time variable which I've defined here. I'll pass that into this parameter. After doing that, I'll proceed to define my equation as usual. Write the equation k dot, this derivative is written as y dot dt because we have the y dt with respect to time equals minus t multiplied by y. Again, the m dot option dot I mode is equal to 4. And here we are solving with display equals false. And after getting the solution, we plot m dot time, we plot y dot value. Let's run this cell and see the result that we have. See, we have this result. So we have the plot of y against time. Here, the solution is not displayed because I've passed in the option display equals false. Now we'll proceed to the third problem, which is estimation of parameter. To do estimation of parameter, we assume that we have some data, experimental data, which we have obtained. And so here I just chose some fictitious data. In the real sense, you have some experimental data. So here I chose a fictitious data, t underscore data. These are my time data, and this is my measured x data. So I'll load that into my namespace. The next thing I'll do is to initialize GEKKO like we've done previously. Now define my time variable by assigning that to t data. And then my x data becomes my control variable. So that's why it's called m.cv. My control variable, the value equals x data. I want the variable to be updated. So I'll define the option f.f status, the solution status, solutions to be updated equals 1. Now, the next thing I'll do is that I will define my fixed variable, which is k, m.fv. Here, I don't pass in any option, just leave it empty, and then define the status to be 1. I want the value to be what? To be fixed. While we are solving this, we are trying to fit the data to obtain the value of k. At every point in time, the value of k should be updated. So f.status equals 1. Next, we define the equation. Now, I'm solving this same equation here from the first problem. Remember here, I solved this problem by, picking a value of x, defining my time space, and then fixing my k. But in this problem now, I don't want to fix the k. So I want to solve the x dt equals minus k multiplied by x squared. But in this problem here, I'm using x. It doesn't really matter. You can use x squared or x. Doesn't really matter. But I want to solve this problem. So what I'm trying to do here is I'm trying to obtain the value of k. So the next is to define our options. I have m.I mode equals 5. In this I mode case, I'm not solving the ODE, rather I'm trying to estimate the value of this parameter. More or less, you can put it this way that you're trying to do to fit the experimental data which you obtain the value of k. So the value of m dot nodes, you can decide to choose any node you want. I think the detailed discussion on this can also be found in my first or previous video, which is the episode 7. So I'll choose 5. You can vary it. We'll vary it and see the result I will also obtain by varying it here. So having done all this, we've defined the equation, the I mode, the node. The next thing is for us to solve the problem. And I have m dot solve equals that. Display is false. After solving, I want to print the optimal value and also print the value of k. So that's why I have optimal value m dot options dot objective function value. And on the next line, print k equals to k dot value, because k dot value gives me a list. I'll pick out the first item of that list. It's a single list, but I have to pick out the first item. Otherwise, it will return the result with the square parentheses. So having said this, run this cell when GEKKO is solving it, because I'm not displaying the results, so you can actually see it. So what you see here is the optimal value 2.69 and the value of k is 2.373. You have dynamically obtained the value of k knowing a few point or measured point of the time and the x data. So next we can plot again the predicted versus the measured results in m dot time against x value, and I'm using a blue color line with zero marker. The label becomes predicted. I'll print the value of k. Next, I'll also plot on the same plot m dot time and then the raw x data with a red line, and I'll label that measured data, put in the legend, and define the X and the Y label. If we run this cell, what do we have? We can see the result that we have. That what GEKKO has actually done is to fit the experimental data while estimating the value of K. So we can see here the blue circles representing the predicted, while the red line denoting the measured point. Let's vary this inode and see how the result looks like. Change the inode to 10 and run again. What do we have? It's running. In a short while, it's going to return the result. The value remains the same, 2.37, 2.69. Let's plot again. What do we have? So ideally, increasing the value of the nodes really does not have significant effect on the result. So at the barest minimum, use the number of nodes to be 5. The I node simply refers to the collocation point. I don't want to dive into that in this video, like I mentioned earlier. So the problem now is an optimal control problem. The reason why I started by solving the problem, that progression difficulty progression, I move progressively so that you really understand how we can apply dynamic optimization using simultaneous estimation to solving problems in chemical engineering. So, and now here is a typical problem that we want to solve, having established the foundation. Here we say a batch reactor operating over a 1 hour period produces two products according to the parallel reaction mechanism, A to B, A to C. I think you all understand what I'm saying. Here we have a parallel reaction giving us two products, B and C. Both reactions are irreversible and first order in A, with rate constants giving us, we are given the expression for the rate constant, where I denotes each of the species 1 and 2. Also, where K10 is 10 raised per 6, K20 is given, E1, E2 are all given. Also, watch the unit. We are going to, so when we're solving this problem, we have to make sure that our unit is also consistent in solving this, otherwise we get the wrong result. Now, the objective is to find the temperature time profile that maximizes the yield of B for operating temperatures below 282 degrees Fahrenheit. The optimal control problem is defined as this: maximize B, which is the use of B, at the final time into 1.0. So the final time is, which is TF, is 1.0. if you look at it over a 1 hour period. So, subject to what are our constraints? Because here we are now dealing with a maximization problem. So, we should have our constraints. So, here our constraints are derivatives. So, you can see the reason why I initially started by solving ODEs using the package GEKKO. So, I have the ADT given as minus K1 plus K2 multiplied by A, and the B dt equals K1A. Of course, here we have K1 and K2. So the rate of consumption of A is given as this rate of consumption of B, or production of B, is given also here. And furthermore, okay, at time t equals 0, the value initial value of A is A naught, while that of B is 0. So how do we solve this problem? So let's go to solution 4. First, I'll call GEKKO by assigning M, which is like standing for my model, an abbreviation, equals GEKKO, and I want remote to be true. If you don't define remote to be true, by default, remote is true. The next thing of course, I know the value of my A naught. A naught is 2.0, though not stated in the problem, but you can just assume 2.0. Or for any other problem, the value will be given to you, the initial concentration of A 2.0. Now I define my number of time interval as 101. Now the operating time is 1.0, as I call T under OP 1.0. Next is m dot time. Then I'll take, remember, linearly spaced vector between 0 and the operating time for how many times, this number of time steps. So what this has done is that what the time space is now defined, and here becomes a variable under as associated with what the model m. Now let's define other variables now, so that GEKKO can understand the variables that we have and that we're dealing with in this problem. In this problem, how many variables do we have? We have A variables, we have B is a variable. Remember, K1, K2 are also variables, but K1, K2 are also function of other variables, E, E1, E2, R, and T. So we come here and define A, M dot val. That's how you define variable in GEKKO. Value equals A naught. Initial value is A naught. B has initial value of 0. Then we define T also as variable because the rate constant is a function of temperature. So I will choose initial value of 282 degrees Fahrenheit, value 282. Then define the value of R. R is a parameter, not a variable. There's the difference between parameters and variables. I think I also talked about it in my previous video, and I think you should watch that video. M dot parameter value equals, this is the gas constant. Now, because my activation energy is in cal per gram mole, I have to choose the value of R to be consistent with that unit, which is 1.982. And then I'll define here P. Okay, P is just a placement. And I use that to define the finite time point. Just like I want to, how do I explain that here? Is that I want to store all the time points while solving this problem. And to do that, I choose P and I define it to be the number of zeros of the time interval. So I have 101 zeros. Now, the final value, which is the last time point at which I want to optimize the yield or maximize the yield of B, which is P of minus 1, will now be assigned to be time underscore OP, which is what? The operating time 1.0. Now, the final time here, which I'll call T final, you will see the reason why I'm choosing these terms very shortly. T final equals M dot, I'll define that parameter and then I'll pass that in as what? As P. Now, notice I have 101 zeros array, okay, of time interval. Now, I've replaced the last time point with what? With 1. So I now have all zeros until the 100th position. The 101 position becomes 1. And then that becomes my new array for my final time, which I'll define as a parameter. Now, notice that we have K1, K2, they are also expressions. Now, when you have expressions like this, we refer to them as intermediate equations or intermediate expressions. So to be able to solve this derivative, you need to know that expression. So I'll call that as K1 and M dot intermediate. That's how we define that. So it's easily with GEKKO, you can actually define this seamlessly and solve your problem. So what is that M dot intermediate? I will define what the intermediate is, and that's 10 raised per 6 multiplied by M dot all mathematical operations that you obtain that you can get from NumPy or SciPy. You can also obtain that from GEKKO. For example, the exponentials, the trigonometric functions, just name them. So here I have M dot exponential, then put in my E1, I know the value, divided by R and T. So long as I have defined those variables R, T, A, B, GEKKO understands all of this. So first of all, define variables, follow the order in which I'm defining the problems. First of all, state what you know, from what you know to what you don't know, and then GEKKO can easily pick and solve this problem. Likewise, you define K2 in similar pattern. After doing that, the next thing you do is to define your equations now. What are my equations? The A dt. So I have equation A dot dt. Now notice that I have, what do I have on this side? Look at what I have here. You can decide to transfer this A here, so it becomes the A dt divided by this. It doesn't really change that. Now, what I've also done here is that I've non-dimensionalized A by dividing with A naught. You will see the aftermath effect of that when I plot the results. So I define A dt divided by A naught equals minus K1, K2 multiplied by A. Likewise, I have M dot equation B dB dt divided by A naught equals that. Because the problem talked about maximizing the yield, and so I had to divide both derivatives by the initial value of A. That's the reason why I did that. So next is to call the maximization problem. Remember in the previous examples or in previous problems, we went straight to solving the equations that we have defined. But here, what we're interested in is to maximize B at the final time point, at T final. And because we are solving a maximization problem that involves derivative, our mode is equal to 6. All of these are also detailed in my previous video. You can watch it to see an extensive discussion on the GEKKO, the modes, the different solution that you have. Now, notice that what we're actually doing here is an optimal control problem with maximizing the yield of B. So in GEKKO, the mode to be used to solve is 6, and the next we solve our problem. If we run this cell, the solution is on. By default, I'm solving, and you can see the result being printed down the procedures that is being implemented in solving this problem. It tells you are solving dynamic control with interior point solver. I intentionally left the solver to print the results so that you understand what is going on. So you can see all the iterations is doing that. If GEKKO does not find a solution, it will tell you also if it fails to find a solution, it will return that report. So you can see how many iterations it's doing, 119. It's completed 140 iterations. You can see the objective functions, scaled and unscaled. I will not go into all of these, but our interest is look at the final value of the objective function, and we have a successful solution. So we can then plot the yield of B, the value of B with respect to time. Run that cell, what do we have? It gives us this. Because the values are quite small, I decided to use a semi-log plot. So I plotted semi-log y. In other words, the y-axis is logged while the time axis is linear. So having said that, we move to the next problem, and I think this should be the last problem for this episode. Here we are dealing with a shell and tube heat exchanger with that has a total cost of C equals $700 plus 250 D raised to power 2.5 multiplied by L plus $200 DL, where D is the diameter in feet and L is the length in feet. If an inequality constraint exists for the heat exchanger as defined here, find the optimal values of D and L. This problem is taken from the same textbook that I've been using, that I've used in all my videos. Watch it from episode 1, 2, 3, 4, 5, 6 until 8. Same textbook that has to do with process optimization, Himeblau. That's where I got this problem from. So let's look at the solution, which is solution 5. A GEKKO to use a remote server. And then define my variables. That's the next thing. What is my D? M dot val. I just assume a value of 12. Here I've assumed the initial estimate L equals to 0. You can likewise change it to 1. Mind you, at the end of this video, I will leave a link of this notebook in the description so you can download it, use it to practice while you are watching this video. And then if you have any question, please leave it in the comment section. So next, I'll define the equation. Now, this equation here is the inequality constraint. Now, in GEKKO, we can define both equality and inequality constraint. The next thing is to now define the problem. What's the problem we are looking at? We are looking at an optimal cost of heat exchanger, right? So in other words, we are trying to minimize the cost. So we need to know the optimal values of D and L that minimizes the cost. When you are carrying out optimization on certain process equipment, for example, the heat exchanger, you're actually interested in trying to reduce the cost of the heat exchanger. And so having said that, we define that which is here. Okay, we're given that expression. Now the I mode to solve is 2. Running this cell, GEKKO will run using the remote server. It says model parameter estimation with interior point solver. Remember, problem 4 specifically states that we are solving a control problem. Here, we are solving a model parameter estimation problem. So it goes down, down, down. You can follow through. The number of iteration here is 27, and it says optimal solution found. The solution was found. The final objective function value is 15,376.69. So that's the final objective function. So I can print the optimal value of the diameter, likewise the length. So how do I print that? D dot value would extract the value of the optimal diameter. But you can see in parentheses I have 0 because it returns a single list. And so I will extract the first item of that list, and that's why you have 0 here. Likewise, I'll do the same for L. And then finally, I'll print the optimal value in cost. In other words, the optimal cost. I have a dollar sign is in dollar. M dot options dot objective obj FCN value, objective function value. That's the meaning. So if we run this cell, it returns the optimal diameter should be 1.37 feet. Optimal length should be 10.21 feet, and the optimal cost of the heat exchanger with those dimensions is 15,376. With this, we have come to the end of this video, and here I've just demonstrated for you how we can use GEKKO to do dynamic optimization. GEKKO, the package GEKKO is quite very valuable to solving a lot of problems. You can do real-time optimization problems, solve real-time control problems using the package GEKKO. If you have any question, please leave it in the comment section. If you also want me to discuss or make videos on other topic, you can also suggest that using the comment section. If you're just watching my video for the first time, please smash the like button, share this video with your colleagues, share with your friends, and do not forget to subscribe to my YouTube channel if you have not subscribed. And when you subscribe, hit the notification bell so that whenever I release new videos, you will be notified. Until then, I will see you in my next video. Bye.